In a world so thirsty for energy, it's a wonder why so much of it gets wasted. One of the most common byproducts of industrial processes is hot water. The heat in that water is energy that, more often than not, gets thrown away. We want to harness that excess energy and give it a new life. We want to get as much out of the stream as we can. The biggest issue we face when we have a stream like this one is the low quality energy it contains. In our case, it is only around 200 degrees Celsius. At temperatures like these, there are limited ways to harness the energy. The way we harness the low-grade heat is via thermochemical energy storage. If we're clever, we can use a reversible exothermic-endothermic reaction. By heating the reactants, we can drive the reaction forward, and by removing the products, we can prevent the reaction from reversing. Then, later, when we want the thermal energy back, we simply recombine the products and allow the reverse reaction to occur. This allows for nearly indefinite storage of thermal energy. The reaction that is chosen should occur at temperatures a little below the waste heat and have a high energy density. It is also advantageous if the products are easily separable, so reactions where the products are different states of matter are preferred. For example, if a solid reacts to form a solid and a gas, the gas is easily separated from the solid.
Our goal has been to build computer simulations using COMSOL multiphysics that account for the complexities of the fluid flow, heat transfer, and reaction kinetics needed to design the reactors used to convert waste heat. Recognizing that reaction requirements will be different for every situation, our team set out to create two configurable models, a time-dependent solid-gas reaction and a steady-state liquid-gas reaction. COMSOL multiphysics uses finite element analysis to solve systems of coupled partial differential equations. This allows for the numerical simulation of very complex problems with complex geometries and complex couplings. Here is a simulation of a cat with hot whiskers and a cold nose. In our system, heat is consumed in a reaction that occurs in a moving fluid. This reaction proceeds at a rate determined by both temperature and concentration and produces multiphase products, which are physically separated by the moving fluid. All these things need to be modeled simultaneously, which is nearly impossible to do analytically. Here, we modeled the first 7 days of a solid time-dependent reaction, where a salt with a high affinity for water is stored in a porous matrix. By flowing hot air through this salt matrix, we can drive off all the water and simultaneously cool the air. Later, we can flow humid air through the reactor, reintroducing the water to the salt, drying the air, and recovering the stored heat.
Salt hydrates are the typical candidates for thermochemical energy storage, but it is often preferable to work with the steady-state process. The team has also created a liquid-gas model that would operate at steady-state conditions. The model is shown here as a concentric, countercurrent shell and tube heat exchanger with a single tube. There were several options considered for this scenario. The first was ionic liquids, which don't actually react with water but can still produce some heat from mixing and separation. Another was the decomposition and reformation of acetals from an aldehyde and an alcohol. This would be a steady-state process, but would also require the separation of aldehyde and alcohol for actual storage of the energy. These models are designed to be fitted and changed according to the different requirements of an individual reaction. There are many potential reactions for both a solid matrix model and a liquid gas model, and both of the models shown here can be used as a starting point for characterizing a variety of different thermochemical energy storage systems. Thank you.